So rational functions, they are quotient, okay, of polynomials. Okay. So in other words, so rational functions, they have the form, so f of x is equal to p of x over q of x, okay, where p and q, p of x and q of x are polynomials, So for example, examples of rational functions, example, so f of x, so as I said, just a polynomial on the top. So for example, 3x cubed minus x squared plus x minus 1 over, let's say, x power 7 minus x power 5 plus 3x cubed minus 2, for example. Okay, so in the top, that's a polynomial. That's my p of x. So this is my p of x, my polynomial p of x. And in the denominator, that's my polynomial q of x. This is my polynomial q of x. Okay, so both p and q are polynomials. So that's why my f is a rational function, right? So both p and q are polynomials. So then f of x is a polynomial. Sorry, is a rational function. Okay. Another example, which is not a rational function. So as I said, in polynomial, guys, the powers, they have to be positive integers or 0. So like for example, if you have let's say f of x equal to, let's say, square root of x plus 1 over x squared minus 2. All right, and then the numerator is not, it's not a polynomial, right? This is supposed to be p, this is supposed to be q, right? Q of x. P of x, is not a polynomial because the square root of x is like x to the power 1/2, and 1/2, it's it's a fraction, it's not a whole number, right? It's not a positive integer. So p of x is not a polynomial, okay, because square root of x, that's like x to the power 1/2, and this power is a fraction, it's not positive integer or 0. Okay, so this is not a positive, this is not a positive integer or 0. Okay, it's a fraction, right? So then f of x is not a polynomial. Okay, so f of x, yeah, so sorry, if f of x is not a rational function. I don't know why I keep saying polynomial. So f of x is not rational, is not a rational function. Rational function. All right. What else? Yeah. So a third example, let's say you have f of x equal to 1 over x. Okay. So this is p of x, and this is q of x. Okay, so do you think, guys, this is a rational function or not? Do you think p and q both are polynomial? Well, I mean, for Q, it's just x to the power 1, right? So that's a positive integer. Actually, the answer is yes, Lorden. So Q is polynomial. I mean, that's clear from because it's just x, which is x power 1. But P is also a polynomial because, as I explained a couple of days ago, I guess. So P of x, P of x, which is 1, but then the constant one, you can write it like x to the power 0. Okay, so then, yes, constant is actually a polynomial. Yes, Lorden. So absolutely, so a constant is a polynomial. That's so a constant is a polynomial. Polynomial because the power of b is 0. The power is 0, and that's allowed. So it's either positive integer or 0. Okay. So yeah, so in this case, so P of x is a polynomial. So P is a polynomial, and so f of x is rational function. Is rational. All right. Last example, number 4. Well, let me see. Of course, if you have a negative power, guys, like f of x, let's say x cubed minus x over, let's say x minus x to the power negative 1. Okay. So this is, as usual, this is P, this is Q, all right? Then you have to be careful. So this, Q is actually not a polynomial because you have a negative power. So the Q of x is not a polynomial because of the negative power. Is not because of the negative power. Because of this x here to the power negative 1, and so that's a negative power, negative integer. Okay, so then f of x is not rational. Any questions, guys, about rational functions? So it's just a quotient of polynomial functions, right? Yeah, and one more remark, guys, about the graphing rational functions. The domain so if you have a rational function, so f of x, let's say, is p of x over q of x. So this is a rational function, is rational, right? Then the domain of f, because this is a quotient, right? We have a division, right? This is a division right here. Okay, then the domain of f of x okay, so because we do have a division, we don't have a square root because remember in the polynomials we cannot have a square root, right? I said that because that would be like the power would be like a fraction, not a positive integer, right? So we don't have a square root in a rational function, but we do have a division, right? And if you have a division, of course, the domain would be any number or any real number x except where the denominator is 0, right? So the domain would be any real number x except any real number x except where q of x is 0. Q of x, that's the denominator, right? So we have to exclude the values where the denominator is 0. Okay. All right, so I'm gonna show you a couple of examples, guys, of rational functions. I'm gonna do like very basic rational functions. I'm gonna show you how to graph such rational functions, and we'll see a couple of examples, right? So let me start with a very basic example. So let's start with the example. Um, so I'm gonna take the example. And then sorry, no, it's Candace. Oh yeah. Okay. Okay. I will send you an email. All right. Okay, so let's take 1 over x, guys. This is a rational function, of course. This is rational. It's rational because, you know, as we said, the numerator is just a constant, and we said the constant is a polynomial, and obviously x in the denominator it's a polynomial, right? Okay. So this function f, first, what's the domain of f? Domain of f, of course, domain of f of x. Well, in f of x we have it's a division, right? So we have to solve denominator equal to 0, and we have to exclude the answer from the domain, right? So, sorry. So domain of f of x. So we have to solve denominator equal to 0, and denominator is just x, so it's just x equal to 0. All right, and so we have to exclude it from the domain. Right, so the domain of f of x would be like any real number except the 0, right? So domain of f of x, so let me write down the answer here for domain. So domain of f x is any number except this 0. So it's like negative infinity, 0 excluded, union 0 excluded, positive infinity. Okay. Anyway, so let's see what happens when so f is not it's not defined at x equal to 0, right? F of 0 is undefined, right? So if you exclude 0 from the domain, it means that f of 0, this is undefined. It doesn't exist, right? So f of 0 is undefined, right? It's 1 over 0, so it's undefined. So there's no output which corresponds to 0, okay? It's undefined, doesn't exist. All right. However, let's see. So what we're gonna do now, guys, we're gonna try to see what happens to the graph of x when x approaches 0. Okay, so first question. So question 1, what happens to the graph of f x when x approaches 0. Okay, when x, so instead of approaches, I'm gonna use like an arrow. Okay, so x approaches 0. Okay, so this arrow here means that x approaches, so this is approaches. So what do I mean by approaches 0? It's like you are on the number line and you are trying to get close to 0, right? You are getting closer and closer to 0. Okay, you approach 0. And well, of course, so when you are on the number line and this is 0, right? You have your number line, you have 0, and you want to try to approach 0. Okay, so there are like two different ways to approach 0. You can approach 0 from from the left, or you can approach 0 from the right. Okay, so either you get close to 0 from the left, or you get close to 0 from the right. Okay, and so we're gonna distinguish between these two cases. So I'm gonna write, so when I write x, so here, let me write it here. So here x approaches, so x approach 0 from the left, right? And here x approaches 0 from the right. Okay. Now, as I said, we're going to distinguish between these two cases. So notation for that would be like, so x approaches 0, and I'm going to put the minus sign here in the top. So this is not like negative. This means, this minus here means that the value of x approaches 0 from the left. So this is, so x getting close to 0 from the left. Okay, and if you put the plus in the top of 0, so if you put like, if you write like x arrow 0 and a plus, okay, this means that x getting close to 0 from the right. Okay, so this is, I mean, this is just a notation, guys. So again, the arrow means you are approaching, well, 0, it could be, of course, it could be a different number. Instead of 0, it could be 1 or 2, or, okay, it could be any number. The minus, this minus here means that you are approaching the number from the left, and the plus, it means that you're approaching the number from the right. Okay, so it's just again, it's just a notation. Now, as I said, the question is, what happens to the graph when you approach, what happens to the graph of f when x approaches 0? And as I said, there are two ways to approach 0, either from the right or from the left. So, okay, so when x approaches 0 from the right, okay, so you are like in his number line, this is 0, and you are trying to get very close to 0. So let's say you are like 1, and then 1, and then I'm gonna take like 0.1, and then I'm gonna take like 0.01, right? So I'm getting close to 0, right? And then I can take like 0.001, etc. Right? So I'm getting close to 0. I'm not equal to 0, never equal to 0, but I'm getting close to 0. Okay, and let's see what happens to the values of f of x, right? So here's my x, here's my f of x, which is 1 over x, right? So let's say x is 1, and then x is 0.1, and then x is 0.01, x is 0.001, right? So you see, guys, here in the values of x, the values of x, as you can see here, like 1, 0 0.1, 0 0.01, 0 0.001, etc., 0 like 3 zeros, 1, etc. So you are getting close, very close. You are approaching 0, right? So here we are approaching 0. So x up is approaching 0. So here x approaches 0. Approaches 0 from the right. From the right side, because as you can see here, right? I mean, on the right side of 0, it's positive, right? So that's why it's from the right, because these values are on the right side of 0. Okay. Now, what we are interested in is the values of the function f. So when x is 1, f of x, of course, is just 1 over 1, which is 1, right? So this is 1 over x. So if x is 1, then f of x is just 1 over 1, which is 1. When x is 0 0.1, what will be 1 over 0 0.1? So 1 over 0 0.1. That will be 10, right? So that will be 10. When x is 1.01, 1 over 0 0.01, that will be 100. When x is 0 0.001, 1 over x would be like 1,000. Right? So this is now 1,000, right? And you can imagine, like, you can continue, like, next would be like, it would be like 10,000, next would be like 100,000, 1 million, right? 1 million, etc., etc., right? So my question for you guys, so what happens to the values of the function f as x approaches 0 from the right? So as x approaches 0, as you are getting close to 0 from the right, the values of the function f, they are getting larger and larger, right? Like 10, 100, 1,000, 1 million, 10,000, so they're getting larger and larger, right? And larger means that you're going to go to very, very large numbers, right? So then you're going to go to infinity. So what we are saying here, guys, that as x approaches 0 from the right, the values of the function f, the function f of x, of course, these are the values of the function f here are positive. So the values of the function f are approaching positive infinity. So the values of f of x are approaching positive infinity, because, as I said, these values are getting larger and larger. So you go like from 1 million, 10 millions, etc., 1 billion, etc., etc. So you're getting larger and larger, and then so it's you're approaching infinity, right? Because you think of infinity like a very large number, right? Very, very large number. All right, so the conclusion here from this table values, guys, is that as x approaches, as x approaches 0 from the right, the function f of x approaches positive infinity, right? Because the values are getting larger and larger, right? Is there any question, guys, about this this conclusion? I mean, I hope you can see from the table the values that as x getting small, the value of the function f is getting very large, right? And again, guys, this plus, it's not like positive 0. This plus means you are approaching 0 from the right. Okay. So like in the graph, So how do we graph this? Okay, so here's my positive infinity. This is a 0. And let's say like you are like, here's 1. This is like 0.1, you know, this is like 0.01, this is like 0.001, etc., right? This is 1 here. Okay, so if x is 1, again, the function f is just 1 over x, right? F of x is just 1 over x. Okay, so guys, this here. So this is here supposed to be positive. So function f is just 1 over x. So we are saying if x is 1, 1 over x is 1, right? Now, we are saying if x is 0.1, x would be 1 over x would be 10, right? So it's like, let's say here's 10, somewhere here. If x is like 0.01, 1 over x would be like 1,000 or 100, right? It's like a very large number here. X is like 0.301, then 1 over x would be like 10,000 or whatever, very, very large number, right? So we are getting very close, a very large number, very close to infinity, right? So as you can see here, the graph, so it's, excuse me? I didn't hear you. I think you, is there any question, guys? Nope, okay. So what I'm saying is that, as you can see, guys, here, my graph, it's getting very close. So it's going up, all the way up, right? But the thing is, let me erase this thing here. We're gonna just write it right here. It's better. This x goes plus. So as you can see, guys, here, all right, my graph, because I'm getting very, very large number as x gets close to 0, I'm getting very, very large number, right? But you have to keep in mind, guys, f of 0 is undefined, right? This is 0, here's 0, right? F of 0 is undefined. So which means that the graph, you see right here, the graph, it doesn't touch the y-axis because f of 0 is undefined. Because if the graph touched the x-axis, the y-axis, then f of 0 would be well defined. So here, the graph, so the graph never touch. So the graph, this is the graph of f of x, of course. So the graph of f of x it's very, very close. It gets very, very close to the y-axis, but it doesn't touch the y-axis, right? So the graph of f of x gets very close. Actually, it gets as close as you want from the y-axis as we want from the y-axis. Okay, but it doesn't touch the y-axis. It doesn't touch, right? It doesn't touch the y-axis. Okay, as you can see, you see my red graph here? It's very close to the y-axis, but it doesn't touch because, again, if you touch the y, because f of 0 is undefined, okay? Because f of 0 is undefined. So you are not supposed to touch the y-axis. Okay. Does this make sense to you guys? You see what I'm saying here? I mean, so the graph of f, it's very, very close. It gets as close as we want from the y-axis, here, right? But it doesn't touch the y-axis because we are not, f of 0 is undefined. If it touch the y-axis, it means that f of 0 is well defined, but it's not. Okay. Right. So that's for when x approaches as x approaches 0 from the right. Now, what happens when x approaches 0 from the left? Well, it's the same thing, but instead of positive values, we're going to have negative values. So, okay, so now what happens to f of x, to the values of f of x as x approaches 0 from the left? Okay, so what does it mean approaching 0 from the left? You know, we have like here's -1. Let's say this is -0.1. This is, let's say, a -0.01. You know, this is like -0.001, etc., etc. So we are getting close from 0, but from the left, because I mean, we have negative numbers here, -1, -0.1, they are negative. So they are on the left side of 0. So we're approaching 0 from the left, right? So if you make a table of values with the x and the f of x, so x and f of x. So we can see, guys, the same thing here. F of x, of course, is 1 over x, right? So if x is you know, -1, if x, then you're approaching 0 from the left. So I'm going to take like a smaller value, so a -0.1, -0.01, etc., -0. Like 2 zeros or 3 zeros, 1, etc., etc. Right? We are getting close to 0, but never equal to 0, because 1 over 0 is not defined. 0.0000001, for example, etc., etc. As you can see here, so x is again approaches 0 from the left, because they are negative numbers, right? And what happens to the values of f? Let's see. So if x is -1, 1 over -1, of course, is going to be -1. 1 over -0.1, that's -10. Like next would be like -100. Next would be like -1000. Next would be like -1 million, etc., etc. Next would be like -1 billion as x gets close to 0, right? So the values of x, they are approaching, as you can see, -100, -1000, -1 million, -1 billion, etc., etc. So then values of f of x, they are approaching -infinity. Okay. Now, in the graph, if you want to plot these points, let's see what happens. Right, so here is my 0, but now I have my -1 here, negative, I don't know, 0.1, -0, -0 point, like 3 zeros or 2 zeros, 1, etc., etc. Right, this is my -infinity here. So this is -1, for example. So like when x is -1, 1 over x would be -1. When x is -0.1, then that would be -10. Negative, I don't know, 100, -1 billion, 1 million, -1 billion, -2 billions, etc., etc. So you can see here. So again, I'm going to have the same phenomenon. So it's your graph. So you can see here the graph is getting as close as you want from the, you know, from the y-axis. You know, this is vertical axis, this is my y-axis. Okay, so as you can see here, it gets very close as we want from the y-axis, but the graph, it doesn't touch this y-axis again, because f of 0 is undefined, right? So so again, the graph of f of x gets very close to the y-axis, as close as we want from the y-axis, but it doesn't touch. Okay, because f of 0 is undefined, because f of 0 is undefined. Okay, so you see what happens, guys. Again, the problem here is that f of 0 is undefined, right? And as you can see, so the conclusion is that, so we have this very special, like, vertical line. So the conclusion, so you have this graph. So we have your y-axis. This is your y-axis, let's say, right? And the thing is, so what happens is that the graph of f, as I said, so it gets very close to this y-axis here, right? And here, okay, but it doesn't touch this y-axis, right? So so the y-axis, guys, what's the equation of the y-axis? Well, the y-axis is the equation of the y-axis is x equal to 0, because if you take any point on the y-axis, the x coordinate is 0. Okay, so the y-axis, that's the same as saying x is equal to 0. Okay, that's the equation of the y-axis. Okay. All right. Anyway, so such a line, like this y-axis here, such a line is called, it has a name, and it's called a vertical asymptote, right? It's a vertical line. I mean, this y-axis, obviously, it's a vertical line. Okay, so such a vertical line is called such vertical line is called a vertical asymptote. Okay. So the idea, guys, in general, so when I say a vertical asymptote, and I'm gonna write the definition of vertical asymptote, but let me just give you first the idea. So what we mean by vertical asymptote is the following. So a vertical asymptote, so you're gonna have like some vertical line, like this vertical line here, okay? And your graph is gonna be like very close, as close as you want from this vertical asymptote, like something like this here. It doesn't touch this vertical asymptote, very close to it, but it doesn't touch it, okay? Or like it could be also on the other side, okay? Or on the other side, like something like this here, okay? Or in the bottom here, okay? Or on the other side would be like something like this here, okay? And again, guys, there's no intersection here, okay? No no intersection. Same here. There's no intersection. So such a green line such a green line is called that's what I call vertical asymptote. So there's no intersection here. No intersection. So that's what I call a vertical asymptote. So your graph is very as close as you want from the vertical asymptote, of course, at infinity, right? Like, you know, at infinity here or at negative infinity here, okay? So now the formal definition of a vertical asymptote. So here's the definition of vertical asymptote. So the line x, so like here, in my example, 1 over x, right? My vertical asymptote was the y-axis, right? Here. Right? My vertical asymptote was this y-axis, and we said y-axis, the equation of the y-axis is just x equal to 0, right? Because it passes through the x equal to 0. Okay. So in general, of course, here it's x equal to 0, but in general, a vertical asymptote is a line with the equation x equal to a. So the line x equal to a is a vertical asymptote if as x approaches a from the left or from the right, could be from the right or from the left, the f of x, the values of the function f, they're going to approach either positive or negative infinity. Okay. So it's like in the graph. So in a graph, so let's say this is your x-axis. This is like x equal to a. Okay, like a could be 0, it could be 1, it could be any number. This is x equal to a. So x equal to a. All right, and so this line x equal to a is a vertical asymptote if for the graph of f if so as x approaches a, so we are like close to a, the graph of f is going to approach infinity. So I am close to a, and the graph is going to go to like to infinity, right? This is supposed to be positive infinity here. This is supposed to be like negative infinity. So the graph is going to be like at positive infinity. So it's going to be, again, as close as we want from the green line, from the vertical asymptote, but doesn't intersect the vertical asymptote, of course. Same here. So it's going to be here at negative infinity, your graph. Very close to your vertical asymptote, but it doesn't intersect the vertical asymptote. Okay. So that's what I call a vertical asymptote. Right. Now the big question, I guess, is how do you find vertical asymptote? So I have this rational function. I have some random rational function. So how do you find vertical asymptote? It's very easy. It's just the solutions of the denominator equal to 0. Okay, so the question now. So in general, so how do we find? So let's say you have f of x, like p of x over q of x, a rational function is rational. Okay, so how do we find vertical asymptote of f? Okay, well, the answer is very short. Just solve denominator equal to 0. So solve denominator, which is q of x. So in general, just solve the denominator, which is q of x equal to 0. Okay, or in other words, solve q of x equal to 0. Q of x equals 0. So we have to solve q of x equals 0. Right, that's where the denominator is 0. All right, that's how we find the vertical asymptote. All right. Any question, guys? All right. Well, as you can probably guess, well, we have vertical asymptote. We also have a horizontal asymptote. Okay, so vertical asymptote, as you can see here, it's a vertical line, right? It's called vertical asymptote because it's a vertical line, right? We're gonna have the same thing. If you just rotate your vertical line, a vertical asymptote to a horizontal line, so then that will be like a horizontal asymptote. So, well, I'm gonna come back to the example with 1 over x. So back to the example, f of x equal to 1 over x. So to find the vertical asymptote, guys, remember, we try to approach, we try to approach 0, right? As you can see here in the table of values, the values of x, they were approaching 0, right? We try to approach 0 from the left and from the right. Now, what I'm gonna do, the values of x, my values of x, are gonna approach infinity. So I'm gonna take very large values of x, and I'm gonna see what happens to the values of f of x. All right, so the question now is, so what happens to the values of f when x approaches infinity, positive infinity, or x approaches negative infinity? So let's see. I'm gonna again make a table of values here. Let's say here's my x, and here's my f of x, which is 1 over x. And now the values of x, they're gonna approach, let's say, positive infinity. So I'm gonna take like very large values of x. Okay, I'm getting closer and closer to positive infinity. So very large values of x. I mean, you can start with the, let's say 10. Let's say x equal to 10. Then I'm gonna take 100, 1,000, 10,000, etc., 1 million, and then let's say 1 billion, etc., right? So I'm getting close to positive infinity, right? Think of positive infinity as like very, very large number. So the values of the values of my x that are getting larger and larger, right? So this is, so here x approaches positive infinity. Now, what happens to the values of f? Okay, let's see. So 1 over 10, that would be 0.1. 1 over 100, of course, that's 0.01. 1 over 1 over 1,000, that would be 0.001. 10,000, that would be like 3 zeros. 1, 1 million, there'll be like 5 zeros, 5 zeros, 1, 2, 3, 4, 5 zeros and 1, and 1 billion would be like, I don't know, I think 8 zeros or something, 8 zeros and 1. Okay. Anyway, so the point is, you can see the values of the function f. They're getting smaller and smaller, right? And they're approaching, as you can guess, from 0, right? So the values of f of x here, as you can see, f of x, the values of f of x, they are approaching 0. They are not equal to, they cannot be, the f of x cannot be equal to 0. And that's really important. So f of x cannot be equal to 0. It cannot be equal to 0. Okay, because I mean 1 over x, if you want to solve 1 over x equal to 0, there is no solution, right? Because if you have a fraction equal to 0, then you're supposed to solve like the numerator equal to 0, but the numerator here is 1. It's never 0. So 1 over x, it's never 0. So this is never 0, right? This is never ever 0. Okay. But as you can see, the values of the function f, they are getting smaller and smaller. You are approaching 0. You are approaching 0 as close as you want from 0, but never equal to 0. Okay. So let's see in the graph. If you want to graph like these points. So in the graph, you're going to have like, oops, the other side, I guess. So in the graph, you're going to have like something like, let's say here, here's 10, for example. This is 100. I don't know, this is 1,000. This is like 10,000. This is like 1 million. This is like 1 billion, etc., etc. So we are approaching positive infinity, right? This is say this is 0, of course, but then you have like here you have like 0. I don't know, 5 zeros or whatever. This is like 0.01 or something, right? Very, very small numbers. And so what we are saying, guys, and this is, let's say, I don't know, 0.1 here, right? Anyway, so the point is, so if x is 10, f of x is 0.1. If x is 100, then f of x would be like 0.01. So we're getting close to 0. 1,000, 1 over 1,000 would be like 0.001. 0.3 zeros 1, 0.5 zeros or 8 zeros. We're getting close to 0. So the graph is going to be like, you can see you're getting close. You're getting close to the x-axis here, because the values of the function, they're supposed to approach 0, right? But you don't touch the x-axis because f of x, it cannot be 0. So here again, there's no intersection. Because f of x cannot be 0. Okay, so your graph is getting very close to the x-axis this time. So getting as close as we want. So the graph is getting as close as we want from the x-axis. From the x-axis, right? From the x-axis. Okay, but as I said, it doesn't touch the x-axis. I mean, it seems like it's not possible, but it is possible, right? So, um, and you can imagine the same thing if you approach. So this is when x approaches infinity, then the values of the function f, they're gonna approach 0. And so we can do the same thing, of course, when x approaches negative infinity. Okay, so so you can imagine here. So conclusions that so as the values of x approaches, uh, positive infinity, the value of the function f, they approach 0, right? That's what we said, like from the table. As you can see, the values of x, they're getting larger and larger, so they are approaching positive infinity. And on the other side, the corresponding values of the function f, they're getting smaller and smaller, and actually they're getting very, very close as we want from 0. But it cannot be equal to 0 again, right? As close as we want from 0, but never 0. And you can imagine, I mean, if you take like negative large numbers, like as x approaches negative infinity, you're gonna have the same thing. F of x is gonna approach 0, like negative 0. So such a line, so in this case, you see the x-axis here. So this x-axis here, so it's very, very close as we want from the, so the graph is as close as we want from the x-axis, but it doesn't touch the x-axis. So the x-axis in this case is called horizontal asymptote. So this is what I call a horizontal asymptote. So what's the equation of the x-axis? Of course, the x-axis, all the points, they have their y coordinate equal to 0. So the equation of the x-axis is just y equal to 0. So again, what's the idea of this horizontal asymptote? So the idea is the following: when you have a horizontal asymptote, what happens to the graph is the following. So you have your graph. This is x-axis. This is your y-axis, and we have, this is a horizontal asymptote. Okay, and what we are saying is that, so this green line is your horizontal asymptote. So when you have a horizontal asymptote, so as x approaches positive infinity or negative infinity, so we are at positive infinity here. This is negative infinity, of course, right here. So when your x is at positive infinity, the graph is going to be very close to your horizontal asymptote. So you're going to have like something like this here. Okay, or it could be on the other side. Depends, of course, on the graph. Okay, so this is your graph. This is f of x. Or at negative infinity, you could have something like this here. So if you have horizontal asymptote, then you're gonna have like something like this. Okay. So that's what I call a horizontal asymptote. So again, the graph, it doesn't touch. You are not allowed to touch the graph. You are not allowed to touch the horizontal asymptote. Okay, but your graph is going to be as close as you want from the horizontal asymptote. Okay, so this is supposed to, of course, to get closer and closer to the horizontal asymptote, but it doesn't touch. Okay, so here again, no intersection. Doesn't touch, so no intersection. So that's what I call a horizontal asymptote in a graph. No intersection. Okay. Now the formal definition of the horizontal asymptote, I can write it down for you. So definition. Well, I mean, as you can see here from what we are saying is that, so you're going to have a horizontal asymptote if, so as x approaches positive infinity or negative infinity, your values of function f, they're going to approach some number. Well, here it's a 0, but it could be any number, finite number. So definition is the following. So the line oops. So the line y equal to a is a horizontal asymptote okay if, so as x, as you can see here, your x is approaching infinity, either positive or negative. As x approaches either positive or negative infinity, the values of the function f, they're gonna approach some finite number. So they're gonna approach this a. They're gonna approach a. Well, here in the example with 1 over x, it approaches 0, right? In this example, 1 over x approaches infinity. 1 over x would be very close to 0, right? But it could be a different number than 0, right? It doesn't have to be 0. So it could be just a number, some number a. So that's what I call a horizontal asymptote. All right, guys, I know it's too much information here, but we're gonna use this horizontal asymptote and vertical asymptote to graph our rational functions. Now, so the question now, of course, how do we find the horizontal asymptote, right? It's simple. I mean, how do we find the vertical and horizontal asymptote? I mean, it seems like the first time when you see this, it seems complicated, but actually it's not. I mean, of course, once you know how to find the asymptote. So question now, of course, how do we find horizontal asymptote? So, I mean, for vertical asymptote, you could have like, because that's the solutions of denominator equal to 0, right? So it depends on how many solutions in the you have when you solve denominator equal to 0, right? For the vertical asymptote. The horizontal asymptote, there's a good news. You could possibly have like one horizontal asymptote or no horizontal asymptote. Okay, there is no more than one horizontal asymptote. So how do we find horizontal asymptote of the rational function of f of x equal to p of x over q of x, right? F is a rational function, p and q are polynomials. Well, there are 3 cases. So case 1, if degree of p, if degree of the top is strictly larger than the degree of the bottom, then there is no horizontal asymptote. Okay, so if degree of p of x is larger than degree of q, the denominator, degree, again, guys, that's the highest power of x, right? The degree, again, just to remind you, degree, that's so degree, that's the highest power of x, power of x. Okay. So if degree of p is larger than degree of q, then there is no horizontal, then there's no horizontal asymptote. Okay. Actually, in Calc 1, you'll see why this is true. Because, I mean, what we are doing here, guys, is like a sort of what we call the notion of limit. Okay, so we're gonna study limit, notion of limit in Calc 1, and that's what we are doing now. We'll see in Calc 1 why, like if degree of P is larger than degree of Q, then there's no horizontal asymptote. So the proof of this, we'll see the proof of this if you take Calc 1, right? So case number 2. So the other way, if degree of P is less, less than the degree of Q, then there is a horizontal asymptote, and it would be just the x-axis. So then the x-axis is a horizontal asymptote. Okay, or y equal to 0. That's the x-axis. Y equal to 0. Y equal to 0, that's the equation of the x-axis. Last case, when the degree of P is equal to the degree of Q. So case the degree of P is equal to the degree of Q, then we do have a horizontal asymptote, and the equation would be then y equals to leading coefficient of P of x over the leading coefficient of Q of x is, so this line would be horizontal asymptote coefficient of Q. So this line is a horizontal asymptote. Okay, so to find, so what I'm saying here, guys, to find the horizontal asymptote, you have to compare the degree of P to the degree of Q. So if the degree of the top is larger than the degree of the bottom, there is no horizontal asymptote. Degree of the top is less than the degree of the denominator, then the x-axis is going to be horizontal asymptote. If they have the same degree, then the horizontal asymptote would be like the leading coefficient of P over the leading coefficient of Q. All right. So yeah, so that's how we find the horizontal asymptote, and that's actually the last piece of information you're going to need to graph rational functions. So we're going to need the vertical horizontal asymptotes, and then we're going to need the x and y intercept. Okay, and then I'm going to show you how to use all these informations to graph your rational functions. All right, so now we can move. So we're going to apply everything that we learned now to some examples. So, okay, now the big question, of course, the goal of this section is how to graph rational functions. So, graphing rational functions. So we're gonna need okay. So we need to find first, of course, we need to find the vertical asymptote. Two, you need to find the horizontal asymptote. And three, you need to find the x-intercept. Okay. And so this is like what we did for polynomial and quadratic functions, right? So find the and finally find the y-intercept, of course. Okay. All right. So let's do an example. I'm going to show probably more than one example because, as I said, vertical horizontal asymptote, it could be sometimes could be tricky. So let's do a couple of examples, and I'm going to show you how to graph your rational function. Examples. So example one. Example one, I'm going to just take, say, f of x equal to, let's say, x minus 1 times x plus 1 over x minus 2 times x plus 2. Okay. So this is my function f. My function f, of course, it's so the top, that would be my p of x, and the denominator, that would be my q of x. All right. So this is a rational function because, of course, p is a polynomial. I mean, if you multiply x minus 1 by x plus 1, obviously you're going to have a polynomial. So there's p is a polynomial. Same thing for q. I mean, you multiply x minus 2 by x plus 2, you're going to have just like a combination of powers of x. So that's also a polynomial. So my f of x here is a rational function. Okay, so f of x in this case is a rational function. Anyway, so first thing we're going to do, guys, so we're going to find a vertical asymptote. Okay, so 1. So we're going to find a vertical asymptote. So how do we find vertical asymptote? Just solve the denominator. Okay, let's just solve a denominator equal to 0. Okay, that's how we find the vertical asymptote. Right, so the denominator is just x minus 2 times x plus 2, right, equal to 0. And so either x minus 2 is 0 or x plus 2 is 0. So x minus 2 is 0, then of course x is positive 2, and x plus 2 is 0, then x is negative 2. So I have two vertical asymptotes. So the answer here, as you can see, it's quite simple. So the answer here, so we have two vertical asymptotes, a vertical asymptote. So VA, of course, stands for vertical asymptote. So vertical asymptotes are, so we have x equal to 2 and x equal to negative 2. All right, so that's just the answer. Okay. So yeah, before the horizontal asymptote, guys, I'm gonna just explain here what do we mean by x equal to 2 and x equal to negative 2 to be a vertical asymptote. So like you have your graph, so just this is the idea here. I'm just trying to explain what do we mean by having x equal to 2 and x equal to negative 2 as vertical asymptote. So like you are at x equal to 2, this is x equal to 2, and this is x equal to negative 2, right? And then, so we have vertical asymptote. So we have like vertical lines here passing through positive 2 and passing through the negative 2, right? That's my vertical asymptote. And so my graph is supposed to be, this is, of course, is like positive infinity here. and here it's like negative infinity, right? And my graph is supposed to be as close as we want from the vertical asymptote at infinity. So it's going to be like very close here. Well, it depends. It could be at positive infinity, or it could be here in the bottom at negative infinity. Two options here. Or on the other side, so it's going to be close again, or close here at negative infinity. Okay. Same here at positive 2. So either the graphs is going to be as close as we want from our vertical asymptote at positive infinity or at negative infinity. Okay, and here the same thing here on the other side, very close. Graph very close to the vertical asymptote at infinity, right? So that's what we mean by having x equal to 2 and x equal to negative 2 as a vertical asymptote, right? And of course, we're going to use this in the graph, right? When we graph the function f. Next, so that's for the vertical asymptote. Next, we need to find the horizontal asymptote, all right? So we need to find number 2. We need to find the horizontal asymptote. And again, how do we find the horizontal asymptote? We have to compare the degree of P to the degree of Q. So when I find, so we need to compare, so compare the degree of P of X to the degree of Q of X. Okay, so my function f, let me just write down here again. So my function f was like, in the top was like x minus 1 times x plus 1. And in the denominator was like x minus 1 times x plus 2, right? Now the top, that's my p of x, and denominator, that's my q of x. Now, I guess my question for you guys, what's the degree of p? What will be the degree of p? What's the highest power of x in p?
1.
Nope, that's not true, because you know, if you distribute, so p is because you need to distribute here, right? Because like x times x, yes, Lord, it's gonna be 2. So if we distribute p, actually it's not, it's p is like x squared, you know, plus x minus 1. That's my p, right? If you distribute, so the degree of p is actually 2. And the same for q. So it's like q would be like x times x, that would be x squared plus x times 2 plus 2x minus 2x minus 2 plus 2, that's like negative 4. So the degree of q actually, it's 2. Okay. So the degree of p is going to be equal to the degree of q, is going to be equal to 2. Degree of p is equal to the degree of 2, degree of q is equal to 2. And in this case, I mean, for the horizontal asymptote, if you have the same, the p and q, they have this the same degree, then the horizontal asymptote, in this case, the horizontal asymptote is y equal to leading
Neighbor B.
coefficient. Excuse me.
That's okay, go ahead.
Yeah, it's the leading coefficient of p over the leading coefficient of q. So what's the leading coefficient of p? Well, that'll be 1, because it's 1x squared, right? And the leading coefficient of q, it's also 1, because we have like 1 times x squared. So the horizontal asymptote is so y equal to like leading coefficient of p P of x over, so leading coefficient of q, and that will be 1 over 1. So the answer will be y equals to 1. So that's equal to 1 over 1, right? That's my leading coefficient, so y is equal to 1. That's my horizontal asymptote. Okay. All right, so I got my vertical asymptote, my horizontal asymptote. Now, well, before the x-intercept, let me explain what do I mean by having y equals to 1 as a horizontal asymptote. So like in the graph, we're gonna have like something like, so the idea is the following. So you have your graph, right? And we have, let's say here's y equals to 1. And this is y-axis, of course. And here you have negative infinity, positive infinity. So your horizontal asymptote, it's a horizontal line. Obviously, it's called horizontal asymptote. So it's a horizontal line. So y equals to 1. So this is my y equals to 1. It's my horizontal. This is y equals to 1, my horizontal asymptote, right? And then, so what happens is that, so let me write it somewhere here. Anyway, so what does it mean to have this y equals to 1 as a horizontal asymptote? Well, then the graph, so when you are at negative infinity or at positive infinity, all right, your x here is here, somewhere here. Here's your x, or at positive infinity, here's your x. So what happens to the graph is that the graph at negative infinity is going to be very close to your horizontal asymptote. Of course, it could be below the horizontal asymptote or above the horizontal asymptote. So like something like this here. But again, guys, it's going to be as close as you want from this horizontal asymptote, but it doesn't touch the horizontal asymptote. The same thing here on the other side at positive infinity, your graph is going to be very, very close, as close as you want from the horizontal asymptote. Okay. So that's what we mean by a y equals to 1 as a horizontal asymptote. All right, so anyway, I'm going to show you later how to use this in the graph. Now we have to find the x-intercept and then y-intercept, and then we're going to graph f. Okay, so next thing to do is the x-intercept. So for the x-intercept, guys, when we have the rational functions, all you have to do, a rational function is like a fraction, right? And you want to solve the fraction. Remember, x-intercept was like to solve f of x equal to 0, right? Solve f of x equal to 0. Now, for a fraction to be equal to 0, it means that the numerator is 0. So for the x-intercept, all you have to do is to solve the numerator equal to 0. And the numerator, of course, that's p of x. So solve p of x equal to 0. And so that would be the x minus 1 times the x plus 1 equal to 0 times. So so either x minus 1 is 0 or x plus 1 is 0. So the solutions are positive 1 and negative 1. So we have two x-intercept at negative 1 and at positive 1. All right, so so the answer here, so x-intercept are negative 1 and positive 1. Okay, that's for the x-intercept. Be careful, guys. So for the vertical asymptote, you solve the denominator equal to 0. For the x-intercept, you solve the numerator equal to 0. Okay, so just be careful. Now, last thing to do, and then we can graph our function f, is to find the y-intercept. and y-intercept is just f of 0 as usual. So evaluate f of 0. Just be careful, guys, here. So f of 0 would be like, f of x is like, x minus 1, x plus 1, x minus 2, x plus 2. So you plug 0 in the function f. So this is 0 minus 1 times 0 plus 1 over 0 minus 2 times 0 plus 2. Just be careful. So this is a multiplication here, right? This is a product because from my experience, I know a lot of students, instead of multiplying, they will, for example, they would add or subtract for some reason. So that's a multiplication, right? So that's like -1 times +1 over -2 times +2. So that would be like -1 over -4. So the answer would be 1/4. So the answer is 1/4. Okay, positive, because there's a negative at the top, the negative in the denominator. So that's positive 1/4. So the answer, y-intercept, is 1/4. So it's 0 and then 1/4. Okay, now we are good. We can try to graph our function f. So that's all the piece of informations we're going to use to graph our function f. So 5, we're going to graph f of x. So let me just write down here the informations we have. So we have vertical asymptote. We know it's, we said it's x +2 and x -2. We had horizontal asymptote at y equals to 1, x-intercept. We said it's x-intercept, it's positive and -1, so positive 1, 0, -1, 0. And the y-intercept, it's the 1/4. Okay. Okay, first advice, guys. When you graph f, you graph from left to right. Okay, this is you graph f from left to right. This is really important. So from left to right, you start from the left, from left to right when you graph. Okay. All right. So I'm gonna draw my horizontal asymptote, my vertical asymptote. I'm gonna plot my x, y-intercept, etc. Right. So let's do this. Okay, so I'm gonna need the +1, -1, so +1 here. This is +2. On the other side, I'm gonna need -1 here, and I'm gonna need -2 here. I'm gonna probably take more space here. This is +2. And then I'm gonna need the 1/4 on the y-axis. This is 1/4. Right? And I'm gonna draw my vertical asymptote. So vertical asymptote, as you can see, guys, here, vertical asymptote, it's at x equal to +2 and x equal to -2, right? So so at x equal to +2. So here's my first vertical asymptote, and x equal to -2. All right. Now I have my horizontal asymptote. I forgot. So here should be 1 here. Let's say here's 1. So 1/4 and 1. So horizontal asymptote, that's a horizontal line, of course. That's y equals to 1. So it's going to be this horizontal asymptote is going to be right here. Okay, so that's my horizontal asymptote. You see 1 here? That's y equals to 1. That's my horizontal asymptote, right? All right, guys. So I'm gonna plot. So this is my x-intercept. So we have 1, 0. We have negative 1, 0, and my y-intercept it's 1/4. Okay. All right. So we start from the left, right? So when you start from the left, of course, when you start from the left, you are at negative infinity. Here's my negative infinity. This is my positive. This is positive infinity, and here's negative infinity. You start from the left. You are at negative infinity. So because you have a horizontal asymptote and you are at negative infinity, it means that the graph, it must be as close as you want from the horizontal asymptote at negative infinity. Okay. Um, so it's going to be as close as we want from the horizontal asymptote. But the thing here, there's a problem here. This is why the graphing rational function is tricky. Because here, like, there are two options, right? We are supposed to be close to the horizontal asymptote, but there are like two options here. The graph could be like above the horizontal asymptote or below the horizontal asymptote. So my graph of f, it could be like above the horizontal asymptote, like this, very close here, right, to the horizontal asymptote, or below the horizontal asymptote, very close but below the horizontal asymptote, right? So here, like, there are two options for my graph, right? So I have to figure out which one is the right one. Okay. So what I'm gonna do, okay, I'm gonna just say, well, I have these two options. So next thing, what I'm supposed to do next? Well, if you go from left to right, next thing is you're gonna have your vertical asymptote, right? As you can see, the vertical line, I'm gonna have my vertical asymptote. And if you have your vertical asymptote, then your graph is supposed to be as close as you want from your vertical asymptote. So my graph is supposed to be like, of course, at positive infinity. So it's supposed to be here, right? Or the other option is that my graph is close to my vertical asymptote, but like at negative infinity in the bottom. Okay. So here it looks like, guys, we have like two options for our graph. It could be like you start from above the horizontal asymptote and you go like this to the top, all the way to the top, or you start from below the horizontal asymptote and you go down here. And again, guys, we are not supposed to intersect at infinity. You are not supposed to intersect the horizontal asymptote here, right? Here, you are not supposed to intersect your horizontal asymptote. So that's why we have like two options. Either you go all the way up, okay, to my next vertical asymptote, or we go all the way down to my vertical asymptote. Which one do you think, guys, would be the correct graph? The one above the horizontal asymptote or the one below the horizontal asymptote?
I think the one on top, but I'm not sure.
You're right, the one in the top. And the reason is, so if you pick the one in the bottom, the thing is you're gonna cross the
X-axis.
x-axis. And
Exactly.
if you cross the x-axis, it means that you need to have like an x-intercept there. But there is no x-intercept there. So you cannot cross the x-axis here at this point here. There's no way you cross the x-axis there because there is no x-intercept there. Okay, so here, no x-intercept. Okay, so that's why the correct graph would be the one above the.
So let's say that
But if you do have, let's say you have an x-intercept here, right?
all
Let's say
right.
I have a point here. Well, I have to join my x-intercept anyway, right? I have to go down here. Again, I'm not allowed to like touch my horizontal asymptote, right? So I have to go to my x-intercept, right? And then, go all the way down to my vertical asymptote if there was an x-intercept. But there is no x-intercept. So then that's the reason y, the one above the horizontal asymptote would be the correct graph.
And
So
then
that's, yes.
it keeps going up. It doesn't touch the vertical one, right?
Oh yeah, it doesn't touch. Again,
Uh,
that's the idea behind this vertical horizontal. It doesn't, you get as close as you want, but it doesn't touch. That's the thing. It doesn't touch the vertical asymptote. So this is why this kind of the graphing rational function is kind of tricky. So most of the time, guys, you're gonna have like two options. You have just to figure out which one is the correct one. Just you think about it like a couple of seconds, and then you'll be fine. All right, so now the next I'm gonna start again from my my vertical asymptote, and again I'm supposed to be as close as I want for my vertical asymptote. So I'm supposed to be like my graph supposed to be like right here, okay? Or, and again we're gonna have another option. You can start from down here, right? Your graph can be like from down here, close to your vertical asymptote, right, at infinity here. And so again, you're gonna have like two options, right? Now, which option is gonna be the right one? So let's see. If we start from the top, okay. So what do we have to do next? The next thing to do is there's this x-intercept here, right? That's the next thing to do. So I have to join this x-intercept. So I have to go here to this x-intercept, right? And then go up again to this y-intercept. But as you can see, guys, I'm gonna cross, right? I'm gonna cross. If I try to join my y-intercept, I'm gonna I have to cross again the x-axis. So I'm gonna need another x-intercept here, right? But there is no x-intercept there. So the right thing to do is actually is to start from the bottom and join your x-intercept. You start from the bottom here, join your x-intercept, okay, there's no problem. And then next thing is to join your y-intercept, okay, everything is fine. And next thing, I have to join my x-intercept, right? And then I have my vertical asymptote. And then vertical asymptote, again, I'm gonna have like two options. Like I'm gonna be like close to the vertical asymptote. And again, I'm gonna have two options, one in the top, one in the bottom. Which one is the correct one? Well, as you can see, if you got, yes, yeah, the other side, yes, yes, as well. And as you can see, I mean, if you decide to go up, well, you're gonna cross the x-axis, and then you have like, you need to have like an x-intercept there, but there's no x-intercept there, right? Because if you decide to go to the top, so we have to go all the way down. There's no other option. So you have to go all the way down here. And okay, well, I'm sorry, guys. I'm just gonna need like 30 seconds to finish this one. So next, again, the other side, again, I'm gonna have two options. Either you start from the top here or from the bottom here, all right? So I will need to figure out which one is the correct one, but let's check what's the next thing to do. Next thing to do is, this is my horizontal asymptote. And again, I'm gonna have like two options here. So I'm gonna have, so either this graph in here or this one in here. Well, again, which one is gonna be the correct one? Well, the one in the bottom here means that you're gonna have you need an x-intercept right here, but there's no x-intercept there, right? So then the correct graph would be the one here in the top. Okay, so it's all about the x-intercepts, the placement of the x-intercept.
Can be a case that you will have an x-intercept in one side and none in the other one. So let's say
Yeah.
like,
Yes, yes, yeah. We're gonna do more examples next time, all right?
Okay.
So don't worry about it. All right, guys, I'm sorry I went over time. I'm gonna stop here, and next time I promise we're gonna do more examples, all right? Thank you, everyone. And
Professor,
yes. Yes, Rabila.
Can you share the board with me? Like me or
You mean
us?
download the file?
Yeah, yeah.
Yeah, I can do that. Sure, no problem. Yeah,
Oh, thank
I'm
you,
gonna do
doctor.
it right away. I will
Okay,
send you by email.
okay.
All right, everyone. Have a nice weekend. Enjoy your
What
weekend, and I
one
will see you. Yes.
just with how do we know if you have to start from the left or the right? Because you started from the left.
The graph.
Yeah.
No,
You
you
start
always start from the left when you graph the function.
always?
Yeah,
Oh,
always. Just yeah, start from always from the left. Yes.
okay. All right. Okay. All right, thank you.
Yeah, have
Mhm.
a good night, everybody.
Good night, everyone. Yeah, and then yeah, sure. I will email you about the test.
What?
I'm gonna check. I'm gonna check your test. Uh, let's see.
Who?
Who's talking? Let's see. I'm sorry. Elizabeth. No, I'm not talking to you, Elizabeth. I'm sorry.
Oh,
No,
okay, sorry.
no problem.
Weekend.
No, you too.
Thank you.
Thank you, everyone. Thank you, Xin. Good night.
And good night.
All right. Good night, everyone.